So hi, my name is Jonas, and we analyze time domain sketching properties of fruits. So why are we concerned with that? There's a trend in agriculture towards automation, I guess that's clear. And a key component is fruit monitoring prior to harvest, for example, to allow yield prediction or the optimal time for harvesting the fruits. And some fruits do not exhibit their ripeness state visually, like you can see here, for example, with the watermelons, which already look like that when they are really small and unripe. And that's why we're analyzing ultra-wideband radar, which is possibly able to penetrate some outer material layers and to get some information about the fruit flesh itself. So the scope of our publication are laboratory measurements to analyze the variability of the fruit scattering, which is important for a classifier design. So when we want to classify the fruit and what ripeness stage it is, we need to know, does the measurement actually changes when we observe the fruit from 1 meter distance or from a different point of view. And that's why we build up this measurement setup where we place the fruits in the lab on a turntable. We could rotate the fruits in front of our ultra-wideband radar, which operates from 1.4 to 5.6 gigahertz. And we could also change the distance to the fruits. So we acquired lots of data to analyze the dependency on distance and rotation. And we did some pre-processing to make sure that we only analyze the effects of the fruits and not of the setup, of course. So we need to perform some background measurement, which is quite easy for the setup, where we simply remove the fruit to get the background. We did some system equalization to be sure that backscattered signal is not distorted, for example, by the antennas. And then we have here the three most important results. On one hand, we see that the scattering of the fruits is quite dispersive, which mainly comes due to the fact that when inner parts reflect, the wave travels through the fruit flesh, which has, due to the high water content, a very high permittivity. And that means that the wave propagation speed is quite low. So the reflection of inner parts will be received quite late, which means that the actual impulse response is really dispersive. And we also found that power relative to the rotation angle varies significantly. So that means when we observe the fruit in the field, we need to actually observe the fruit from different angles to compensate such random power fluctuations. However, the pulse shape itself, so the shape of this reflection is quite stable over distance and rotation. And what is the outlook? So we found out how complex the fruit scattering is, so how we need to perform measurements actually on the field and in the lab for the ground truth. And our goal is multi-sensor fusion with ultra-wideband radar and the camera. And the camera should help to localize the system itself on the field so that we can place information about the fruit which we found in a global reference map, which then helps for farm management decisions. And we performed a promising measurement campaign now in the summer on a watermelon field with lots of watermelons in ripe and unripe state on the field and in the lab. And now the data waits to be analyzed in this way.